So I don't know if I said this before I assigned it, but I started this last semester, and so far I like it. I think it's probably a little unusual, but every problem that I assign this semester, I'm going to assign twice. Okay, and so that was the last assignment. I think was even problems from the first assignment. So the idea is just to ingrain it a little bit. Like you start to forget it, and then you go back and remember it. The same way that, like, ideally, you read your notes, and then before the test, you read them again. It sort of solidifies stuff. It's that same idea. So I'm gonna keep doing that, but I probably should have mentioned it first because I know it's unusual to see, like, well, we already did these, but I want you to do them again. And obviously, like, when I look at your binders, I can't tell whether you really did them again or just copied them. So I mean, I guess you can do what you want, but I think if you try to do them again without looking back at notes, looking back at example problems and stuff, and then see how you did on it after, you'll get more out of it.
So you want it written up again?
Yes, that's right. All the exams are cumulative. Yeah, the quizzes are only from quiz to quiz, but so the stuff that I reassign is eligible on the quizzes. It all makes sense in my head. It's all so simple here, but it seems complicated when I try to make with the talkie talk. Yep. Yeah, I mean, I think you can probably bet that the tests are going to emphasize the new stuff more than the old stuff, but I'm always going to put some old stuff on because I want you to keep going back and refreshing. I don't know, like, we've all had classes where you do well in the class, but then 3 months later, you don't really remember anything. And that's just what I'm trying to, address. Just try to make you keep banging on the stuff, and then it sticks better. Yep. Yes, I think so, right? Yes. Yeah. I don't have them with me though. Yeah, that's true. You do need it for your binder. Yeah, so okay. But there's no statics binder, so you don't need it for that. Ooh, that's extra credit. All right. Any other questions? After the next exam. Yep. Next Thursday is the next test. Lord Almighty. What? I don't like to do that, but okay. Well, we better think about what's going to be on that test then, huh? Well, let's go up through linear interpolation for the test. That sounds good. We'll do that today. We'll have some time to think about it. Okay. So, for real, next Tuesday? Wow, I'm glad you said that. So what would that be? And the topics will be everything up through linear interpolation. And it's cumulative. So everything before that. And then I thought the thing was the binders were you turned them in with the test, but it said the next day. Is that right? Okay, I'm glad you're here. So binders are due Thursday, the 5th, and we're going to cancel I think there's a quiz that would be scheduled the Thursday after that, but that's the one that's canceled. So, because you won't have your binders to study for probably all of that, but I'll be sure to get the binders back the next Thursday. And then the notes that you take and all that kind of stuff, the homework, you can put it in the binder when you get it back the next Thursday. You know, that's how those 3-ring binders work. Put it in later. Okay. Yeah. Well, that's exactly. That's why you can't use a 3-ring binder for a lab notebook. Also, because you can just put in stuff that's like, oh, I invented time travel in 1981. You know. Yep. Yeah, I mean, it's everything. I actually, I think. Mm-hmm. Okay. Either I will do that, or I will assign a that you outline stuff, and then you'll do it for yourself. Okay. All right. So linear interpolation. I think this is basically the picture I drew before, but if you have a function of one variable, and okay, so and you know the values here, so let's say this is f of x, and so you know that this point is x1, f of x1, and you know that this point is x2, f of x2, and you want to estimate the value of, you know, the f value there at x. The way you do that is you assume that this function f is linear between x1 and x2, and then you use that assumed linear function to give you the value here. So this would be the value, you know, this is x, f of x. That's the true thing. This one is x, you know, something like f. That's our approximation. Yeah, and we're going to do that too. Well, we're going to do it with 2 variables. We only need 2 because the substances that we're dealing with, if you know 2 of these properties, that's enough to specify anything else. But the way it works with 2 variables is, so okay, let me just describe it and we'll talk about it more later. But basically, so you have to, we'll do that later. Let's just do it in 1D first. So we're going to make the assumption that y, or the function value is equal to the function value at x1 plus y2 minus y1 over x2 minus x1 times delta x, where delta x in this case would be the distance between x1 and x. So this is x minus x1, and that's our delta x. Okay, so for example, when would you need to do this? I mean, so I'm going to do this example that, so we're going to say, how well does linear interpolation approach approximate a quadratic function? Quadratic. In this case, and so we're going to, so we'll say that the real underlying function is x squared. But we're just going to use the fact that f when x is equal to 1 is equal to 1, and f when x is equal to 1.5 is equal to 2.25. These are the givens. This one wouldn't be known when you're using this, because if you knew it, obviously you wouldn't have to approximate it. You just plug in. And we're trying to find, so, what's f at 1.4? Okay, somewhere in between those two. Well, if you knew what the function was, you just take 1.4 squared. So this would only be useful if you didn't know what the underlying function was. What's the case where that might happen? Well, for us, it's in these tables. Really, it's anything where you're getting your data from experiments. You might make assumptions about what the underlying function is, but if all you have are finite data points, you don't have any proof of what the underlying function is, and that's when this would be useful. Okay, so f at 1.4 is equal to f1 plus f2 minus f1 over x2 minus x1 times delta x. And so let's just plug in those values. F1 is 1. F2 is 2.25 minus F1 is 1 divided by 1.5 minus 1. And what's delta x? 0.4, yep. And you get 1.25 over 0.5 times 0.4 plus 1, and it just gives you 2. How does that compare to the underlying quadratic function? Yep, exactly. So f of 1.4 is equal to 1.4 squared 1.96. And, you know, you could fit a cubic or whatever. You could fit any kind of polynomial to those two values. If so, you know, just based on those two values, there's nothing that specifies what that underlying function is. That was sort of in our head, you know. How could you, so if you're doing an experiment and you want better precision than that, how could you get a better approximation? Yep, exactly. Yep. So the closer you pinch those values together, the better that linear approximation is. That's the whole idea behind numerical analysis. If you want more precision, you make your grid finer, and you know, as time goes by, the computing cost of doing these calculations with a finer grid goes down really quickly, you know. So where in the 80s, say, doing numerical calculations with a really fine grid, you know, took a lot of resources, you know, you can, on the computer on your desk, you know, you can do calculations that have a much finer resolution now than you could then with supercomputers or whatever. Any questions about that idea? Okay, so how would you use this in a thermodynamics problem? So here's another example. So at a temperature of 63 degrees Celsius, what's the pressure? And the specific internal energy. First, for saturated water vapor. And then second, for saturated liquid water. Okay, so first we're going to do it for saturated water vapor. So I'm going to add the table for saturation. Let's see. We're trying to calculate the pressure given the temperature, and so we want to use a table that's indexed by temperature. Okay, so use this. So from this, we can say that the pressure, I'll call it P1, at 60 degrees is 0.19941. This is for part A, so this is for the vapor. The specific internal energy for the vapor is 2456.2. So these are at 60 degrees. And at 70 degrees, we have P2 is 0.31189. U2 is 2469.1. And so, what? Question? Oh. Okay, so the pressure at 63 degrees is 0.19941 plus 0.31189 minus 0.19941 divided by 70 minus 60. And then delta x is 3. And I think if you do that, you get 0.233154. Or if you want it in pascals, that's 233,154 pascals. And then the specific internal energy is 2456.2 plus quantity 2469.1 minus 2456.2 divided by 70 minus 60 times 3. What do you get for that one? $2460.7. No decimal? Okay. Okay. And that is in kilojoules per kilogram. And then for part B, well, why didn't you do part B too? Have you already done it? No, you have to do it from memory. Okay, so so the pressure is going to be the same, but we still have to figure out the specific energy. So for a fluid at 60 degrees, we have 251.61. And at 70 degrees, we have 293.65. And so our estimate for the specific internal energy is 251.61 plus the quantity 293.65 minus 251.61 divided by 70 minus 60 times 3. And what do you get for that? 264.222 kilojoules per kilogram, which is, a factor of 10 lower than for the gas. I don't know. Yes, I'm sure there is. I don't know how to do it. What? Integrate? Yeah, so if you so these had two different, the thing is, what those functions look like for constant values of one of the variables, because we've seen those on those those projections of the PVT surface, you know, like on the temperature versus specific volume graph. There's the vapor dome, and you have something that looks like this, this, this. But with both of those variables, changing, you'd be, if you imagine the PVT surface, you'd be traversing a sort of a diagonal along that crazy complicated curve. And I don't know what that curve would look like. Yeah, I'm sure somewhere online, check it out. I'm not going to do it right now because it would just take minutes of like searching around, but I'm sure there probably is online. You could probably check. That's true. That's a good point. Okay, so why in this case why did we have pressure and specific internal energy as functions of one variable in this case? The whole idea of these simple compressible substances is that if you know two properties, you can figure out all of them. Well, the answer is just that here we're dealing with a saturated material, and you can think of the fact that we're at that phase change, on that phase change line, the boundary of that vapor dome, that sort of fixes our other property. You can think of that as like a property. So this was just because it was saturated. In general, we're going to need two of them, and the two that we're going to use are temperature and pressure. So to find the properties using a table.
Just out of curiosity, what exactly is like some state of
the saturation?
Yeah.
It's a combination of like it's not really fixing one property, but it's fixing a relationship between the properties that just sort of, you can think of it as like constraining it to you're constraining it to somewhere on the surface is what you're doing, To find the properties on the table, you need to specify two properties, and we're always going to do this with temperature and pressure. Now we have linear interpolation for functions of two variables. For functions of two variables. And so in this case, so let's say we have our grid of values. These are X values, these are our Y values. And I want you to notice that the picture I'm drawing here is different than the picture I drew in 1D for functions of one variable. In that one, because it's because we only have one independent variable, the entire function. I draw on the x-axis, we have the independent values. On the y-axis, we have the dependent values. 2D, all I'm drawing is the grid of independent values. Okay, so you have to imagine the functional surface swooping above, you know what I mean? So now so the equivalent of this in 1D would have been if I had just drawn the line, the x-axis, and looked between the points. But now say we want to estimate the value of that function at that point there. Okay, so here's our x1 and our x2. Here's our y1 and our y2. So this is our x. This is our y. And the idea is the same, but we have to do it in 2 steps, or 3 steps in a way. Question? Point slope form. Is that point slope form? Yeah, pretty close. Yep, it is. Yep. So we have to do this in 2 steps. And the steps are first, doesn't matter which variable you do first and which you do second. What I'm calling x and y is arbitrary. But first, interpolate the x values twice. And what we're trying to get here is function value at x, y1, and the function value at x, y2. What we're given, so what would you have to be given to start this process? You have to be given those 4 points of the quadrilateral. So you're given f of, I'll do it in where it is on this grid. So f x1, y2, f of x1, y1, f of x2, y2, and f of x2, y1. Okay, you have to start with those 4 points. So to come up with the function at x and y1, that would be the function of x1, y1, plus the quantity function of x2, y1, minus function of x1, y1, divided by x2 minus x1 times delta x. Okay, so the idea here was that we held y1 constant and then just used the exact same procedure that we did in the one-dimensional case. For the second one, we want f of x, y2, and we'll approximate that as, okay, so tell me, what's this one? Yep, x1, y2. X2, Y2, yep. Exactly. Yep, exactly. Yep. So you see how this pattern's working? Like, so sort of like to save time, I'm telling you a procedure for this. But if you would get $1,000 for inventing a procedure that did this, and you were locked up in a room for a day, you know, like this is probably what you would come up with, you know. So that's the first step. And now what do you think the second step is? Yeah. That is this. Oh, the blue dot here. And then the next thing we did was that blue dot above. So we have these 4 points, and we first use linear interpolation to figure out what those blue dots are, and then we'll use those 2 blue dots to interpolate here at the red dot. Okay, so what's the step now? So now we have everything in x, and we can do the same thing, hold x fixed, and do a linear interpolation between y1 and y2. So here we held y2 constant. And now we'll say f of x, y, the thing that we want, is equal to f of x, y1, plus the quantity f of x, y2, minus f of x, y1, divided by y2 minus y1, times delta y. So in this one we held x constant. Okay, so let's first do this with a function example, and then we'll, yep. Any questions about that?
Say y1 constant.
Mm-hmm.
You're calculating that lower blue dot.
If you hold, yeah, y1 constant, you're calculating the lower blue dot. That's right. And these approximations, again, are, you know, the accuracy of them is just totally dependent on how fine your grid is. Unless you have really jagged functions, but that won't happen here. Not the slope, but I guess anything higher, any higher derivative, whatever, you know, so the concavity, and then whatever you call the third derivative, and whatever you call the fourth derivative and stuff. That's right. If it's just a matter of, like, if it's a linear function, the slope could be 9 million and it would do it perfectly. Yep. That you would put in for what?
For number 2,
Mm-hmm.
X, Y1.
Mm-hmm. The entry, like just this value here. Let's just go through the example, and I think that'll help sort of understand where this stuff comes from. So let's say we're going to approximate this function f of x, y is equal to xy squared. So we're given that f of 1, 4 is equal to 16. F of 1, 3.5 is equal to 12.25. F of 1.5, 4 is equal to 24. F of 1.5 is equal to 18.375. And we want to find f of 1.3 3.6. Yep.
So since we're given a function in this case, we could get it more accurate by using
Yeah, if you have the function, then you know what it is. In a real case where you do this, you don't know the function. You just have it so we can sort of check our result at the end. And so I could come up with 4 points, you know. Okay, so step 1, we're going to calculate f of, so what's x1? 1, what's x2? 1.5. Y1? 3.5. And y2? 4. Yep. So the first thing we're going to do is find f of 1.3, 3.5. So that's equal to f of 1.3, no. That's f of 1.5. We're keeping that y equals 3.5 fixed. Plus the quantity f of 1.5, 3.5, minus f of 1, 3.5, divided by 1.5 minus 1, times delta x, which is 0.3. And so these values are 12.25 plus quantity 18.3 1.3 no f of 1.5 3.5 is 12.25 1.4. Yeah, sorry. So this would be 16, right? With me? Oh no, we're doing. Yeah, getting all turned around. We're doing it in X first. We're holding that Y at 3.5 and we're doing it in X. So this is 18.375 minus 12.25 divided by 1.5 minus 1 times 0.3, and we get 15.925. Right. So that's A, and then B, we want to calculate the function when x is 1.3 and y is y2. So this time y is 4. So we have 16 plus the quantity 24 minus 16 divided by 1.5 minus 1 times 0.3. And I think that gives 20.8. And now the last step is we're going to, now we have these two values for x equals 1.3, and we're going to use those to interpolate. Yep. We're trying to, we're going between, like we're interpolating between x equals 1 and x equals 1.5 to find x equals 1.3. So this is f of 1, 4. This is f of 1.54. F of 1, 4. X2 minus x1, and then x. So I think that's right. So now we're going to say the function of 1.3, 3.6. Okay, so we're going to, so it's going to be 15.925 plus the quantity 20.8 minus 15.925 divided by 4 minus 3.5 times our delta y this time, which is just 0.1. And so we get a value of 16.9. True value for the function we chose. So the true f of 1.3, 3.6 is 16.848. So, you know, that's a pretty big grid, and that's all still pretty close already. Any questions about that? So the first step is you find the, like, visually. So you start out with these. So the function swoops over the top. And you know the function values of these 4 points. Okay? And the first thing you do is interpolate twice to find those two blue dots, the function value of those two blue dots, estimates of those. And then you use those two estimates to find the estimate here. And it's when you think of taking estimates to get your two starting points for another estimate, you can imagine that you want your grid to be pretty small for that to work well. But in this case, it worked, and you know that's a fairly ugly looking function.
It was only a 0.3%
That's good. That's better than any lab you'll ever do. um, well, I didn't bring the last example I was going to do, but so let's just say so let's look at water vapor, and you can see the way this is all organized into chunks, sections. And so what you would use this two-dimensional interpolation process for is if you're going for a pressure between these values. You know, if you get super lucky, you'll do a problem where you have a pressure of 0.35 bar, and then you only have to interpolate in one dimension, right? But if you're between these two, let's say we want to figure out the internal energy, the specific internal energy for water vapor at 0.15 bar. And it's not in this section and it's not in this section. So let's say we want to do 0.15 bar with a temperature of 170 degrees Celsius. So we have water vapor at a pressure of 0.15 bar, or I guess that's 15,000 pascals, and a temperature of 70 degrees Celsius. What's the specific internal energy? Okay, so I'll give you that table. Where is it? You see it? So not compressed water table. I just had it. That's for saturated. So this is for superheated vapor. Maybe is it just not a? Oh, it's a PDF. Okay, so well, I'll just put it up here. Let me just start doing this, at least get through some of it, show the direction. Can someone read off? So I need these four values. P equals 0.06, temperature equals 160 and 200, and then P equals 0.35, temperature equals 160 and 200. Let me write that as 2-1. Okay, can someone read me these 4 values for the internal, specific internal energy? Okay. Mm-hmm. Okay. Mm-hmm. Okay, great. Okay, so step 1. So first I'm going to vary the pressures and keep the temperatures constant. So I guess I'll think of this as, so I'm going to call this one U11, U21, U2, no, 1, 2. Okay, so U, so this is with pressure varying. I'll call this pressure 1. So we'll have 2602.7 plus the quantity 2601.2 minus 2602.7 divided by 0.35 minus 0.06. And then the delta is 0.09. So can someone give me a value for that? 597.3. And then for the second one, we'll vary the pressure and hold the temperature at 200. So this is 2661.4 plus the quantity 2660.4 minus 2661.4 divided by 0.35 minus 0.06 times 0.09. And what do you get for that one? 661.09. And now the specific internal energy at the chosen pressure and at the chosen temperature is 2597.53 plus the quantity 2661.09 minus 2597.53. For both of those? Did you do pressure first or temperature first? Because you could have just as well done temperature first. That's what I did, I think. Yeah, that is what I did. What did you get? And the second one was the same? Okay. Sorry, Fred. Okay, 2602. 2602.23. 2602.23 divided by the change in temperature is 200 minus 160. The delta is 10. And so what do you get for the final answer? 20.95. And that's kilojoules per kilogram. Okay, so in the tonight I'll assign some more problems using this kind of stuff, and there'll be problems where you do this. Once you have the mass of what you're isolating, that'll give you a way to calculate internal energy, and then you'll use the internal energy, use it with the first law of thermodynamics to calculate, whatever you got one equation, you can calculate any one thing.